Come on my dears, last time we had finished all the MCQs in the exercise from chapter number 1. Now I have found 2 questions given in the list of short questions in the exercise in the textbook. They are good one. So I would like to discuss those 2 questions also. In the list of short questions, you please read the statement of number 16. Have you read it? Look now. What is given to us? A coil of resistance R having capital N number of turns connected with a galvanometer having resistance 4R. We are asked to find out the value of induced current because of change in magnetic flux, which changes from capital Phi 1 to capital Phi 2. Okay. Now tell me, according to Faraday's law of electromagnetic induction, you know E equals to minus d phi by dt. So whenever there is a change in magnetic flux, some induced EMF will be developed in the coil. So here also we get some induced EMF across these 2 ends. So what I have done now, remove this coil and in place of coil just place its equivalent battery. So now this coil behaves as if it is a battery of EMF E and internal resistance equal to resistance of the coil. Fine. So in place of this coil, I have shown one battery having EMF E and internal resistance equal to resistance of the coil. And now it is connected with galvanometer. That galvanometer has resistance, come on, 4R. Now tell me, here in this closed path, current will flow from positive to negative this way. Let it be capital I. And you know, according to Ohm's law, induced EMF is equal to current into, better you speak now, effective resistance, because this current will be offered effective resistance from the entire loop. What is that effective resistance? Here we find 4R and R connected in series. For a series combination, what is effective resistance? Simple addition. So 4R plus R, 4R plus R, correct? Minus as it is, change in total magnetic flux, that is final total magnetic flux minus initial total magnetic flux. Upon time interval, I am taking as small t. Fine. Now, if you associate this negative sign inside, then order will be reversed. So, capital Phi 1 minus capital Phi 2. Now, this 4R plus R, that is 5R. If you take it down in the denominator on right hand side, then it is 5R into t. But capital Phi 1 is capital N into small phi 1. Capital Phi 2 is capital N into small phi 2. Okay. Take capital N common, inside the bracket small phi 1 minus small phi 2 upon 5RT, 5RT, correct? What is small phi 1? Magnetic flux linked with only 1 turn in the initial condition. What is small phi 2? Magnetic flux linked with only 1 turn in the final condition. Got it? So this is the value of induced current. Okay. Come on, read very next question, that is number 17. Have you read it? Tell me, what is given to us? We are given 2 circular loop. One is P, another is Q. Both of them having same axis. So both of them are coaxial, having same axis. Not only that, they both are having their planes parallel to each other and at the same time perpendicular to plane of the figure. Plane of this loop is like this, right, this way, that is perpendicular. Here also, for this loop also perpendicular to the plane of the figure, correct? So one loop is like this, another loop is also like this, both of them are parallel, both of them are parallel, fine. Now tell me, what is given to us? When this key is pressed, then naturally current will flow from positive to negative this way, correct? And that current through loop P, I am taking IP. And if you view from right hand side, from here, from point E, if the observer is observing, correct? See this model observer. When he observes, he will find this direction of current through loop P, the direction of current IP is this way, means clockwise. Okay. What is asked to us? What is the direction of induced current in loop Q? That is what we have to find out. Let us find out. Through loop P, if current is flowing this way, correct, clockwise, then where is the direction of magnetic field? For a current carrying circular ring, what you should do? Hold its axis in the right hand palm such that the finger should take the turn in the direction of current this way. Then in that case, whatever direction is shown by the thumb becomes the direction of magnetic field. So right now magnetic field is this way, correct? So if magnetic field is produced here, correct, then this loop Q will have some magnetic flux. Earlier, when this key was open, no current was passing through this loop, no current, no magnetic field, no magnetic flux. So there was no magnetic flux with Q. Now there is some magnetic flux, meaning thereby magnetic flux of coil Q has been increased. Because of increase in magnetic flux, what will happen? We will have production of induced EMF, and because this loop is closed, it will cause the flow of induced current. But according to Lenz's law, direction of induced current should be always such that it can oppose the very cause producing it. And here the cause is increase in the magnetic field. So if that is to be opposed, then it should flow in such a direction such that the resultant magnetic field should decrease. See, here magnetic field is increasing in this direction. To oppose that magnetic field should be produced by induced current in just opposite direction. So in order to have magnetic field in this direction, correct, then current in loop Q, induced current in loop Q should flow this way, that is anti-clockwise. Then only the magnetic field will be produced this way, correct, meaning thereby opposite to earlier magnetic field. That is how the increase in magnetic field will be opposed, and for that sake, according to Lenz's law, induced current should flow anti-clockwise. When you view from point E, that direction of induced current should be anti-clockwise, correct? But mind well, this is the case when key is open and later on you are making the key close. So this is the case when magnetic flux through Q increases, and the reverse case also may be given to you. If magnetic flux of coil Q decreases, then also we will have production of induced current, but that current will be flowing in such a direction whereby it can increase the magnetic field. To increase the magnetic field in this direction, the direction of induced current through loop Q should be clockwise if the reverse is the case. Right now this is the answer. The direction of this current through loop Q, when you observe from here, should be, look here, anti-clockwise, correct? Fine. Now we go for numericals from exercise. Read the statement of first numerical. Read it. Look. First of all, explain me the situation given to you. We have uniform magnetic field perpendicularly inside the plane of the figure shown by symbol of cross. Okay. Now, in that magnetic field we have a square loop having side length say L. Only one side, only one vertical side is inside the magnetic field. The second vertical side is out of the magnetic field. Across these two ends we find that one electrical network of resistors is connected. Fine. What is done now? This loop is withdrawn from the magnetic field. Say it is moved towards the right hand side with constant velocity v. In order to have induced current in this loop by 1 milliampere, what should be the constant velocity of the loop? That is what we have to find out. My dears, first of all, let us find out equivalent resistance between these 2 points shown by symbol P and Q. Can you see here between points P and Q, what is the network? Western bridge. Fine. Now, in this western bridge, let us check whether it is under balance condition or not. Take this as one arm of a western bridge. Take this as another arm of a western bridge. Now, check whether it is balanced or not. In one arm, what is the ratio of resistance is 3/3, that is 1. In the second arm also 3/3, that is 1. So, ratios of resistance is in both the arms along the direction of current are same. So, given western bridge is under balance condition. So, you may disconnect this resistance connected in the diagonal. If you remove this, then this is a series combination now. 3 plus 3, that is 6. Here also 3 plus 3, that is 6. 6 and 6 are connected in parallel between points P and Q. So, what is the equivalent resistance between points P and Q? You know, when identical resistances are connected in parallel, what is the equivalent? Single divided by number. Single is 6, number is 2. 6/2, that is 3 ohm. Correct? Now, tell me, as you move the loop towards right hand side, because of change in magnetic flux linked with that loop, we will have some induced EMF whose magnitude is E equals to BVL. According to Ohm's law, E equals to IR equals to BVL. What is this resistance? This is the effective resistance offered to the induced current. Fine. Find out V now. IR upon BL. V equals to IR upon BL. This current they have given in the statement 1 milliampere. Convert it into ampere, multiply by 10 raised to -3. What about R? That is the effective resistance offered to the induced current. It will be resistance between P and Q plus resistance of the loop through which induced current is flowing. This resistance between points P and Q we have found out it is 3 ohm, and resistance of loop they have given as 1 ohm. So, this total resistance is now 3 plus 1. Okay. What about magnetic field? They are given 2 Weber upon meter square. Side length for square loop is 10 centimeter. Convert it into meter, multiply by 10 raised to -2. Simplify, answer is 0.02 meter per second. Correct? Now, read statement of number 2. Come on, read it. According to Faraday's law on electromagnetic induction, average induced EMF is minus n d phi by dt. Minus n as it is, this is change in magnetic flux linked with 1 turn, final minus initial, upon time interval I am taking t. Now, minus sign if you take inside, the order will be reversed. So, it is now phi 1 minus phi 2 upon t. This n as it is, what is phi formula? A B cos theta When theta is 0 degree, cos 0 is 1. So, phi equals to AB. Instead of phi, when you write phi 1, instead of B, you should write B1. Instead of phi, when you write phi 2, instead of B, you should write B2, because here magnetic field is changing from B1 to B2. So, phi 1 is A into B1, phi 2 is A into B2. Come on, phi 1 is A into B1, phi 2 is A into B2 upon T as it is. And now A and A you can take common, correct? N into A into B1 minus B2 upon T. Total number of tons they have given 200, area of 1 ton 0.12 meter square, initial magnetic field is 0.1 Tesla or Weber upon meter square, final magnetic field is 0.5 Weber upon meter square, and time interval is 0.2 second. Simplify. This answer is minus 48 volt. Negative sign indicates the presence of Lenz's law. In textbook they have given with plus sign, so we should take now modulus. When you take modulus, minus will become plus, so it is 48 volt, correct? Fine. Read now statement of number 3. Read it. Again they are talking about average induced EMF. Formula is minus N d phi by dt. Minus N as it is, change in magnetic flux, final minus initial upon time interval. Come on, minus sign if you take inside, order will be reversed. So it is phi 1 minus phi 2 upon T. N as it is. What is phi 1 formula? A B cos theta 1. A B cos theta 1. Here values of A and B remain constant, theta is changing. When theta becomes theta 1, phi will become phi 1. Similarly, phi 2 is equal to A B cos theta 2 upon T. Now A into B I can take out. Inside the bracket cos theta 1 minus cos theta 2 upon T. Now this NAB as it is, theta 1 is given to you. Look, now this is general formula. Now from this general formula, for 4 different cases given to us, in each case we are supposed to find out this average induced EMF. Let us find out one by one. In the first case, they have given rotation from 0 degree to 90 degree. This theta 1 is the angle between vector A and vector B in the initial condition. Theta 2 is angle between vector A and vector B in the final condition. Come on. In the first case, they have given this angle as 0 degree and final angle between vector and vector B, they have given 90 degree. See, 0 to 90, 0 to 90, 0 to 90 degree. It is a rotation of only 90 degree. If it is one full rotation, how much is the angular displacement in one rotation? 360 degree. Compared to 360 degree, how much is 90 degree? It is 1/4. So if angle or angular displacement is 1/4 of angular displacement in one rotation, then naturally time taken also will be 1/4. What is the time taken to complete one rotation? That is periodic time of rotation, capital T, and it's a fourth part. That's why I am putting T by 4, correct? So this time interval for 90 degree rotation, it is always capital T by 4. Come on. Denominator will become numerator. So 4 will go up. 4 NAB upon capital T. Because cos 0 is 1, cos 90 is 0, 1 minus 0 that is 1, and denominator will become numerator. So it is 4 NAB upon capital T, correct? Now in the second case, we are supposed to use the same formula. Now different values of theta 1 and theta 2. What is the value of theta 1 now? They have given 90 degree and theta 2 value is 180 degree. Again 90 to 180, again angular displacement is of only 90 degree. Again time interval will be T by 4, correct? Fine. Cos 90 degree is 0, cos 180 degree is minus 1, and now denominator will become numerator. So 4 NAB upon capital T, cos 90 is 0 minus cos 180 degree is minus 1. minus minus plus 1 into this will be this only 4 NAB upon capital T. Now in the third case, this angle is given to us 180 degree, this final angle is 270 degree. Again between 180 to 270 degree, that is 90 degree angular displacement, for which time taken is capital T by 4, capital T by 4. Now cos 180 degree is minus 1, minus sign as it is, cos of 270 degree is 0. Denominator will become numerator. So 4 NAB upon T into minus 1, that is minus 4 NAB upon capital T. In the fourth case, this first angle they are given 270 degree, second angle they are given 360 degree, and this time interval is T by 4, because again from 270 to 360, again angular displacement is 90 degree. Come on, cos 270 degree is 0, minus sign as it is, cos of 360 degree is 1. Denominator will become numerator. 4 NAB upon T, 0 minus 1, that is minus 1. If you multiply by minus 1 here, minus 4 NAB upon capital T. Correct? Now sum number 4 is very good sum. Read it carefully. Come on, read it. What is the situation? We are given one extremely long, thin, straight current carrying wire having current I. Come on. On the right hand side of this wire, we have one rectangular loop. Both of these are in the same plane. Fine. And now, for this loop, this much is the length. Let it be capital L, and this height is given to us as B. Fine. What is asked to us? What is the total magnetic flux linked with this entire loop? Let us find out. You know, when current will pass through this wire, it will produce its own magnetic field. And because this loop is on the right side, come on, find out direction of magnetic field. Hold this wire in the right hand palm such that thumb should point in the direction of current. Then, in the manner in which the fingers of right hand palm take the turn, in the same manner magnetic field lines also take the turn. So for this straight wire, the magnetic field lines will be circular and will be getting wrapped over this wire this way. Correct? Circular. So when they are going this way, means they are going inside. So for this loop, magnetic field lines are going inside. Okay. Inside then cross, outside then dot. So you may show some cross symbols here which are going inside. Okay, fine. Now tell me, because of certain number of magnetic field lines passing through this loop which are going perpendicularly inside, it will have some magnetic flux which we have to find out. Okay. First of all, let us do one thing. Let us select one vertical, extremely thin strip having height as B and breadth as dx at distance x from this wire. Okay. This perpendicular distance of this strip is x and the width is this much, which is very small. Let it be dx. This height is B. Now because of this current, what is the magnetic field at all these points, okay, which are located at perpendicular distance x? Come on. For extremely long straight current carrying wire, what is the magnetic field at perpendicular distance y? That you have studied in semester number 3. B equals to mu 0 IE upon 2 pi y. Instead of y, now perpendicular distance is x. That's why I am putting x. Mu 0 I upon 2 pi y. Instead of y, I am putting x. And because magnetic field is inside, I am putting the symbol of cross. Fine. What is the area of this area element? it will be, because it is rectangular, come on, length into breadth. Length, if you take this much b, breadth is dx. Length into breadth, b into dx, b into dx. Area of that area element I am taking as dA. And through this much small area, what is the magnetic flux? Let it be d phi. D phi formula, magnetic flux formula, AB cos theta, AB cos theta. Instead of A, you should take dA, B as it is cos theta, theta is 0 degree because magnetic field is also inside. And for this strip, if you take area vector this way, correct, then it is also inside. Vector A is also inside, vector B is also inside, then naturally angle between them will be 0 degree. Come on, what is B value? I mean, formula of B is mu 0 I upon 2 pi x, mu 0 I upon 2 pi x, dA. What is dA? Come on, b into dx. dA is b into dx, cos 0 is 1, fine. Now take integration on both the sides. Integration d phi equals to mu 0 IB upon 2 pi, because it is constant taken out. Integration 1 upon x dx. Integration 1 upon x dx, fine. Now tell me, when you take summation of partial values of magnetic flux, naturally you will get total magnetic flux. This part as it is, and what is integration 1 upon x dx? It is natural log of x, natural log of x. Now tell me, what is the variable here? Variable is x, because if you shift this area element this way, correct, then x will decrease. If you shift this area element toward the right hand side this way, x will increase. So a quantity which keeps on changing is said to be variable. So right now variable is x. If variable is x, then you should specify the limits also in terms of x. Then you know lower limit of integration is smallest value of variable and upper limit of integration is highest value of variable. When you shift this area element and when you bring it here, the minimum value of x for this edge, it is this much, it is small a, and if you shift this area element toward the right hand side and if you bring it here, then maximum value of x would be this plus this, that is L plus a, L plus a. I mean to say lower limit of integration is minimum value of variable, that is x equal to a, and upper limit of integration, that is maximum value of variable, that is x equal to L plus a. Minimum value of x is a, maximum value of x is L plus a, correct. So you should integrate this function between the two limits. Lower limit is a, upper limit is L plus a. Summation of partial values of magnetic flux will give you total magnetic flux, mu 0 IB upon 2 pi as it is. Integration 1 upon x dx, it is natural log of x from a to L plus a, from a to L plus a. Now this part as it is, you know how to put the limits. First of all, in place of this variable, you should place the upper limit. Natural log of, instead of x, you should write L plus a. After putting minus sign, come on, natural log of, instead of x, we should write a. Now this part as it is, log of this minus log of this. You know log a minus log b, it is log of a upon b, log of a upon b. So natural log of this upon this, L plus a upon a. This gives you final formula of total magnetic flux linked with this entire loop. Okay. Read now statement of number 5. Come on, have you read it? Look, whenever you require to mention the geographic directions in the given problem, you must mention them in the horizontal plane. In this horizontal plane, the direction towards right hand side, you should take it as east, towards left, west, inside, correct? This direction going inward, that is north, and coming outward this way, it is south. Fine. Magnetic field of earth, you can take north south. Okay. what is given to us? One wire is there of length 2 meter. It is falling from a height of 50 meters from the ground. When it is falling, it remains horizontal. Okay. And it remains along east-west direction. In this horizontal direction, there are horizontal components of Earth's magnetic field. Horizontal components of Earth's magnetic field. So this is horizontal component of Earth's magnetic field, and this is the wire. This is the wire which is falling this way. Correct? So when it is falling, it will cut these horizontal components perpendicularly, and because of cutting of magnetic flux, it will have some induced EMF developed across the two ends, which we have to find out when it falls through 20 meters. Let us find out. Come on, here is the magnetic field of Earth. Say this is horizontal component BH, say this is vertical component BV. The direction of velocity of falling wire is vertically downwards. That is why I have shown that direction here. Come on. Angle made by direction of magnetic field with the local horizontal is going to give you deep angle shown by symbol phi. And you know formula of BH studied in semester 3, BH equals to B cos phi. Tell me, what is the third equation of linear motion with constant linear acceleration? V square minus V0 square equals to 2AD. For any freely falling body, V0 is 0. Correct? Initial velocity is 0. Acceleration is equal to gravitational acceleration. Right now they have given 10 meter per second square. This distance through which wire is falling, it is given to you 20 meters. From here you will get V square equal to 400. When you take square root, V equals to 20 meter per second. Fine. What is the formula of induced EMF? I mean motional EMF. What is the formula? Minus BVL. We take right now magnitude plus BVL. But remember, I am showing you one very good idea. How to write this formula I am showing you. BVL, that is true. But please remember, this is that magnetic field or that component of magnetic field which is perpendicular to velocity. Again, here you should write what? That magnetic field or that component of magnetic field which is perpendicular to velocity. Right now, perpendicular to this velocity, it is this component which is BH. That's why I am putting BH. Correct? Fine. Now BH formula is B cos phi. BH formula is B cos phi into VL. What is this capital B? Magnetic field of Earth they have given 0.7 into 10 raised to minus 4 Tesla. Sometimes they may give 0.7 Gauss. Converting Gauss to Tesla, you must multiply by 10 raised to minus 4. Then cos, then what is this deep angle at a given place? They have given 60 degree. This V is the velocity given to you. I mean we have found out. V is how much? 20 meter per second. What about length of the wire? 2 meter. Simplify. Answer is 1.4 into 10 raised to minus 3. This many volt. Suppose they ask in millivolt. Then don't you know? 10 raised to minus 3 volt is 1 millivolt. So it is as good as 1.4 millivolt. Come on my dears. Read the statement of sum number 6. Have you read it? Look. What is given to us? A uniform magnetic field perpendicularly inside the plane of the figure. Fine. There is a linear straight rod of length L which is allowed to fall. Okay. When it is falling because of its own weight, at that time it cuts magnetic field lines. because it is cutting magnetic field lines, we get some induced EMF developed across the two ends of that rod. Let it be capital E. Then you know its formula, E equals to BVL, correct? This is motional EMF by formula BVL. According to Ohm's law, E equals to IR, correct? Fine. Now find out I. It will be BVL upon R. BVL upon R. Now tell me, in this rod, there are electrons which are negatively charged particles. Along with the motion of the rod, they also acquire velocity in downward direction, correct? Now tell me, on electron, in which direction magnetic force is exerted? In the direction of vector B cross vector V. Remembered? Fine. Vector B is inside, vector V, velocity is right now downwards. So situation is like this. This is vector V, this is vector B, and now you want vector B cross vector V. So vector B cross vector V will give you this direction, correct? So if vector B cross vector V is in this direction, then you can say magnetic force exerted on electron also will be in this direction. Fine. Because magnetic force is exerted in this direction, this end loses electrons and hence it becomes positive, and this end gains extra electrons, so it becomes negative. This is how EMF is developed across the two ends of that rod. When electrons are moving this way, in just opposite direction, you can think of electric current, and in the same direction, you should take the length vector, vector L. Now you know, if a current carrying wire is present in a magnetic field, then it experiences magnetic force given by Ampere's law, vector F equals to I into vector L cross vector B. So let us find out direction of that force. It is in the direction of vector L cross vector B. Vector L is this way, towards right hand side. Vector B is inside. Situation is this. This is vector L, this is vector B. Find out vector L cross vector B. Vector L cross vector B, it will be vertically upwards. That is why direction of magnetic force exerted on this rod is also vertically upwards, whose magnitude is given by Ampere's law. F equals to ILB sin theta, where theta is angle between vector L and vector B, which at present is 90 degree. Come on, F as it is. What about value of I? Come on, BVL upon R. BVL upon R into LB, correct? Sin 90 degrees 1. Now what does this formula indicate? Everything else is constant except V. As the rod falls downwards, its velocity goes on increasing. So naturally, when velocity goes on increasing, this force in upper direction will go on increasing. At one stage, it will so happen that this upward force in magnitude will become equal to weight of the rod, that is mass into gravitational acceleration. And at that moment and then after, when vertically upward force equals to vertically downward force, then resultant force exerted on the rod would be 0. When resultant force is 0, acceleration will be 0, and hence velocity of the rod will be constant. So initially it so happens that velocity goes on increasing. At one stage it becomes maximum, and then after that maximum velocity remains constant. Such maximum and constant velocity is known as terminal velocity of the rod, shown by symbol Vt. Fine. So what we should do? We should write V equals to Vt, and we should write this upward force equal to downward force, that is mg. So in place of F, now I am writing mg, and in place of V I should write Vt. Come on, B into B, that is B square, L into L, that is L square. Instead of V I am writing Vt, T for terminal, okay, and this R as it is. And now tell me, find out Vt. Come on, take this R up, bring B square L square down. Vt will be mgr upon B square L square. Vt equals to mgr upon b square L square. This is the required expression of terminal velocity. Got it? Read now sum number 7. Come on, read the statement. Here we are given one DC circuit in which there is a parallel combination of two inductors having inductances L1 and L2. My dears, this arrow indicates that this EMF is variable. Okay? The potential difference between these two ends is variable. That is what is indicated by this arrow. Fine. Now, at a particular instant of time, suppose total current starting from this battery is capital I, and out of capital I, suppose I1 amount of current flows through first inductor and remaining I2 amount of current flows through second inductor. Now tell me, if at a given point of time there is some change in the value of current passing through first inductor, then naturally we will have some self-induced EMF develop across the two ends of that inductor, and it is given by this formula, E equals to minus L di by dt. Instead of L for first inductor I am putting L1, and instead of I here I am writing I1. Similarly for second inductor, E equals to minus L2 di2 upon dt. Why this E and this E are same? Why these two are same? See, there is a parallel combination of these two inductors, and you know, for the components connected in parallel, potential differences across them are always equal. So here also E, here also E. Okay. Now do one thing. You just replace this parallel combination by only one inductor, and for that inductor, suppose self-induced EMF is E, its inductance is L, and time rate of change of current is di by dt. Fine. Now tell me, what is this capital I? It is the total current, so it must be summation of these two currents, correct? So I must be equal to I1 plus I2. Take d by dt on both the sides. When you take d by dt here, so it is di by dt, here it is di1 upon dt, plus here it is di2 upon dt. What is di upon dt from here? What is di upon dt? It is minus E upon L. Minus E upon L. What is di1 upon dt? Come on, di1 upon dt from here, minus E upon L1. Minus E upon L1. What is di2 upon dt? It is minus E upon L2. Here it is minus E upon L2, correct? Now throughout this equation, what you can cancel? Minus E, minus E, minus E, you can cancel. So left is 1 upon L equals to 1 upon L1 plus 1 upon L2. And now take LCM, it will be L1 into L2. Here it will be multiplied by L2. Here it will be multiplied by L1. Now take reciprocal. So L will be equal to L1 L2 upon L1 plus L2. L equals to L1 L2 upon L1 plus L2. Wait. We have got the required expression of equivalent or effective or resultant inductance out of parallel combination of two inductors having inductances L1 and L2. But in general, for n number of inductors connected in parallel, if their equivalent inductance is L, then in general the rule is this: 1 upon L equals to 1 upon L1 plus 1 upon L2 plus dash 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 plus 1 upon Ln. Okay, fine. Now read statement of sum number 8. Come on. You know the formula for self-inductance, capital L equals to capital Phi upon capital I. But what is capital Phi? N into small phi, N into small phi, N into small phi. correct? Now for first coil, which is A, I am writing here LA, here NA, here phi A, and here IA. What is small phi A? It is the magnetic flux linked with 1 ton of coil A. Total number of tons in coil A, they have given 600. Magnetic flux linked with 1 ton of coil A, they have given 1.2 into 10 raised to minus 4 Weber. And current passing through first coil, they have given 3 ampere. Simplify, answer is 24 into 10 raised to minus 3, this many Henry. Okay. Suppose they ask in millihenry, then you know 10 raised to minus 3 Henry is nothing but 1 millihenry. Okay, so at that time it will be 24 millihenry. Now they have asked mutual inductance of two coils. Come on, capital M, you can find out phi 2 upon I1 or phi 1 upon I2. But here we have taken the suffix as A and B. So what I am writing here, phi B upon IA. When you pass current through coil A, and if there is magnetic flux linked with coil B, then we take the ratio this way, it is going to give you mutual inductance. Fine. You may take phi A upon IB, but current passing through coil B is not given to us, so we have to find out using this formula only right now, phi B upon IA. Now what is capital phi B? It is NB into small phi B upon IA, as it is. Small phi B means magnetic flux linked with 1 ton of coil B. What is total number of tons in coil B? 300. This is magnetic flux linked with 1 ton of coil B. They have given 9 into 10 raised to minus 5 Weber. Current passing through coil A, they have given 3 ampere. Simplify, answer is 9 into 10 raised to minus 3 Henry or 9 millihenry. 9 millihenry. Fine. Read number 9. Come on. We are given one toroid in which the radius of toroid is suppose capital R, and if you take cross section of the toroid, then you are going to get circular area. That circular area I am taking capital A equals to pi into small r square, where small r is radius of cross section of a toroid. Fine. Now tell me, if radius of a circle is r, what is this circumference? That circumference gives you length of toroid. It is 2 pi into capital R. Pi value is 3.14. Radius they have given 10 centimeter. 10 upon 100, that is 0.1 meter. Simplify, answer is 0.628, that many meter. Come on, A equals to pi r square. Come on, pi value 3.14, small r. Radius of circular cross section of toroid, they have given 2 centimeter. 2 upon 100, that is 0.02 meter. It's a square. Answer is 0.001256, this many meters square. And now tell me, they have asked about inductance of this toroid. And that inductance, in one of the illustrations in this chapter, we had derived formula of inductance of an inductor. What was that formula? Capital L equals to mu 0 n square A by small l. Come on, mu 0 is permeability of vacuum. It is 4 pi into 10 raised to minus 7 Tesla meter upon ampere. Total number of tons they have given at present 1.5 into 10 raised to 4. It's a square, don't forget. Capital A 0.001256 meter square. What about small l? Small l value is 0.628 meter. Simplify, answer is nearly 0.57 Henry. Nearly 0.57 Henry. Okay. Read number 10 now. Come on. We are given two circular loops which are coplanar and concentric out of which one is very large and in comparison with that another one is very small. That very large circular loop I have shown here and very small I have shown here. The bigger loop we take loop number 1, smaller one we take loop number 2. Come on. This smaller loop has radius, say small r, which is very much smaller than radius of bigger loop. Suppose we pass current I1 through first loop. You know, through any circular ring, if I1 amount of current is passing, then you can expect magnetic field at the center. How much? What is the formula? B equals to mu 0 I upon 2A. Come on, instead of I am putting I1 and what is upon 2A? What is A? Radius. Radius of the bigger loop is capital R. So instead of A, we must write capital R. This much magnetic field is produced at the center. Now, when you pass current this way, come on, if you hold this axis of this loop this way and if you just hold it in your right hand palm, then fingers are taking turn in the direction of current, then this thumb will show you direction of magnetic field. It is right now perpendicularly outward. That's why I have put here dots. They indicate magnetic field lines coming outward perpendicularly from the plane of the figure. And now tell me, actually this much magnetic field is existing only at the center, but this smaller ring is such a small one that it can be considered almost point-like. So same magnetic field you may consider at all the points on the cross section of this small ring. Fine. If it is so, then what is the magnetic flux linked with this small ring? Magnetic flux formula for 1 ton, AB cos theta. AB cos theta. Theta is 0 degree because magnetic field is also perpendicularly outward and area vector also is perpendicularly outward. Angle between these two vectors in the same direction is 0 degree. Come on, what is area of smaller ring? It is pi r square. Pi into radius square. Radius is small r, so I am writing pi into small r square. What about capital B? Mu 0 I1 upon 2r. Mu 0 I1 upon 2r. Take this I1 in the denominator. So phi 2 upon I1 you can find out. It will be mu 0 pi r square upon 2r. Mu 0 pi r square upon 2r. What is this phi 2 upon I1? It is magnetic flux linked with a second coil divided by current passing through first coil. Such a ratio will give you mutual inductance of those two coils. Here mutual inductance of these two loops, and let it be shown by symbol capital M. Formula is right now mu 0 pi r square upon 2 into capital R. Got it?